Good morning and a warm welcome to programmes from BBC Learning Zone. Coming up today, programmes for schools. This morning the focus is on maths. Later at 4 o'clock we cover space, shape and data handling. Before that, this third maths programme of bite-sized revision deals with some other mathematical areas.
Hello, I'm David Bull and welcome to this, the third programme in the series designed to help you with your maths revision for the Key Stage 3 tests in May. As with any test, it's a good idea to plan your revision as early as possible, and this programme can help to get you started. You can work your way through all the units or concentrate on the areas where you feel that you need the most practice, replaying units in bite-sized chunks and trying questions as often as you like. And along with these television programmes, there's also a book and the Key Stage 3 Bitesize website to give you more examples and questions to try out at home. This 2-hour programme has units covering number, graph work, handling data and probability. Between each section you'll see this menu, so you'll know what's coming up and where we've got to. Each section also has a start time, so you can use the on-screen clock in the corner to guide you if you want to fast forward to the parts you need the most help with. So, let's get on with number. This section on number is split into 2 units, one on powers, roots and index notation, and the other on ratio. Let's start with powers, roots and index notation. First, some definitions. Square numbers are formed by multiplying a number by itself. You can think of square numbers in terms of the area of a square. Let me show you what I mean. This square area of bathroom wall needs a splat of tiling. Let's begin down here with 1 square tile. If we add some more tiles, we get a square shape again, with 2 tiles along here and 2 tiles along here. The tiles now cover an area of 2 times 2. That's 4 square tiles. Let's add some more tiles to make a bigger square. That's 3 tiles by 3 tiles. So the area of the square is 3 times 3. That's 9 square tiles. Add some more tiles. 4 tiles by 4 tiles covers an area 4 times 4. That's 16 square tiles. And 5 tiles by 5 tiles covers an area of 5 times 5. That's 25 square tiles. For more information, over to an expert.
That pattern of numbers, 4, 9, 16, 25, is called square numbers. 2 squared, or 2 times 2, equals 4, and that's because a square of length 2 on each side has an area of 1, 2, 3, 4 square units. 2 squared equals 2 times 2 equals 4. 3 squared, or 3 times 3, equals 9, because a square where each side is 3 units has an area which equals 9 square units. 3 squared equals 3 times 3 equals 9. Now here's an interesting question. 1 squared. What does it equal? Well, 1 squared is 1 multiplied by itself, or 1 times 1 equals 1.
You need to know all the square numbers up to 100. That's up to 10 times 10. So, here they are. Now, we're going to move on to look at square roots. Square roots are the opposite or inverse of squares. Let's go back to our expert to hear about them.
2 squared equals 4. Working backwards from that, the square root of 4 equals 2. We can write that like this. 3 squared equals 9. Working backwards from that, the square root of 9 equals 3. We can write that like this. Now we already know that 1 squared equals 1. Working backwards from that, the square root of 1 equals 1, which is the same. We can write it like this. The square root of 1 equals 1.
Now let's move on from squares to cubes. Cube numbers are formed by multiplying a number by itself and then by itself again. Just like you can think of square numbers in terms of the area of a square, you can think of cube numbers in terms of the volume of a cube. So a cube with length 2 units, width 2 units and height 2 units has a volume of 2 times 2 times 2, which is 8 units cubed. So 2 cubed equals 8. A cube with length 3 units, width 3 units and height 3 units has a volume of 3 times 3 times 3. That's 27 units cubed. So 3 cubed equals 27. 4 cubed is 4 times 4 times 4. That's 16 times 4, which is 64. And 5 cubed is 5 times 5 times 5. That's 25 times 5, 125, and so on. So what's our old friend 1 cubed? Well, that's 1 times 1 times 1. That's 1 again. You should at least know 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and 10 cubed. So you should be able to recognise 1, 8, 27, 64, 125, and 1000 as the cubes of 1, 2, 3, 4, 5, and 10. Now, there's a short way of writing a number squared or a number cubed. We can write, for example, 4 squared, that's 4 times 4, as a 4 with a small 2 just after and slightly above it, like this. It's a small 2 because we're multiplying 2 number 4s together. 4 cubed, that's 4 times 4 times 4, can be written as 4 with a small 3 just after and slightly above it. It's a small 3 because we're multiplying 3 number 4s together. Writing a number with a small number after it is called index notation, and the small number itself is called the power or index number. For more, here's our expert.
You might be asked what 8 to the power of 2 is. That's 8 with a little 2 after it. And that 2 means that there are 2 8s multiplied together. 8 times 8. What does that give us? 8 to the power of 2 equals 8 times 8, which is 64. A common mistake is to think that 8 to the power of 2 is the same as 8 times 2. It's not. 8 to the power of 2 is 8 squared, or 8 times 8, which equals 64. 8 times 2 equals 16.
So index notation is a kind of shorthand with that power or index number telling us how many times we're multiplying a number together. This system goes beyond squares and cubes.
We already know about 9 to the power of 2, which is 9 squared, or 9 times 9. 9 to the power of 3 is 9 times 9 times 9, or 9 cubed. 9 times 9 times 9 times 9 can be written 9 to the power of 4. Instead of writing 9 times 9 times 9 times 9 times 9 times 9 times 9, we can write 9 to the power of 7. When the numbers get complicated, we can use a calculator. One way to calculate 9 to the power of 7 is to actually multiply 9 by 9 by 9 by 9 by 9 by 9 by 9 7 times. That's actually 4,782,969. But if you have a scientific calculator, you can calculate it using a special power button on it. You press 9 to the power 7 equals, which gives the same answer with 4 button presses instead of 14.
And that's something you can try out with your own scientific calculator. Your calculator, whatever type it is also useful when finding the square root of a number.
To calculate square roots on a calculator, there's a special square root button, which is here. So let's find the square root of 169. On the calculator, you press 169 followed by the root button. On some calculators, you have to press the square root button first, then the number, then equals to get the answer. And the answer is 13.
So grab your calculator and see how it works out square roots for you. In fact, every number has a square root, not just the familiar ones like 1, 4, 9, 16, 25, and so on. To work out the square root of 12, enter 12 and then press the square root button. And the answer is 3.46411016. Now, if we were to round this off to 2 decimal places, then the answer is 3.46. OK, now on to a test question about powers, roots and index notation. Here are some number cards. They show us the numbers 3, 2 to the power of 6, 81, 8 squared, 64 and 8. Now answer these questions. Part A, which card shows the number that is 9 squared? Part B, which card shows the number that is 2 cubed? Part C, which card shows the number that is the square root of 9? Part D, which card shows a number with an index number of 2? And finally, Part E, which 3 cards show numbers that are equal to each other? Stop the tape and have a go at that yourself. For the definitive answers, let's go to the lead chief marker for Key Stage 3 Maths.
We are shown cards that display the numbers 3, 2 to the power 6, 81, 8 squared, 64 and 8, and asked some questions. Question A asked, which card shows the number that is 9 squared? 9 squared is 9 times 9, which from your times table is 81. Question B asked, which card shows the number that is 2 cubed? 2 cubed is 2 times 2 times 2. And again, from your times table, 2 times 2 is 4, times 2 again is 8. Question C asked, which card shows the number that is the square root of 9? Remember that the square root of 9 is the number that when squared, that's multiplied by itself, gives 9. The answer to that is 3, because 3 times 3 is 9. Question D asked, which card shows a number with an index number of 2? Remember that an index number, or power, is the small number just after and slightly above the main number. So the card with an index number of 2 is the one with a little 2 just after it. So the card we're looking for is 8 to the power 2, or 8 squared. Finally, question E asked, which 3 cards show numbers that are equal to each other? Let's look at 2 to the power 6, which is 2 times 2 times 2 times 2 times 2 times 2. Working that out is 64. Then we have the card 81, so that's no good. Look at 8 to the power 2, which is 8 squared. That's 8 times 8, 64 again, so we're getting somewhere. Finally, we have the card 64 itself, So that's it. The three cards with numbers that are equal to each other are 2 to the power 6, 8 squared, and 64.
For a summary, let's go to the key points. Square numbers are formed by multiplying a number by itself. So the square of 3 is 3 multiplied by 3, which is 9. The square root of a number is the inverse of squaring. It's what you have to multiply by itself to give that number. So the square root of 9 is 3. Cube numbers are formed by multiplying a number by itself 3 times. So the cube of 2 is 2 multiplied by 2 multiplied by 2 again, which is 8. The power of any number tells you how many times the number is multiplied by itself, and it's shown by a small index number. So 2 to the power of 6 is written as a 2 with a little 6 slightly to the right and above it. And finally, remember there are special square root and power buttons on your calculator to help you work them out quickly. Okay, that's it for powers, roots and index notation. There's more information on our website. And if there's anything you don't understand, you can always rewind the tape and play it again. The next section is on ratio. In Programme 1, we looked at the unitary method. This was where we found out about the cost of one thing as a step to calculating or finding out the cost of more than one thing. It's useful when converting between currencies, for instance. Extending this idea, we're going to move on to ratios. Ratios are about the proportions of one quantity to another. Take a look at this clip.
These are to eat today, and these are for the deep freeze. I've no idea how many raspberries I've picked altogether, but I do know how I've been filling these 2 boxes. 1 to eat, 1, 2 to freeze. 1 to eat, 2 to freeze, and so on. 1 to 2, 1 to 2.
So the ratio of raspberries for eating to raspberries for freezing is 1 to 2. Okay, so ratios can be used when quantities vary, but they have to be kept in the same proportions. Take this recipe, for example. It says to make 12 pancakes you need 3 eggs, 900 millilitres of milk and 300 grams of plain flour. So what would happen if I altered the quantities? For that, let's go to our expert.
To make 12 pancakes, we need 3 eggs, 900 millilitres of milk, and 300 grams of flour. We can represent this as a ratio for eggs to milk to flour, which in this instance would be 3 to 900 to 300. Now, if we wish to make double the number of pancakes, then we need double the quantities. So we would have 6 eggs, 1800 millilitres of milk, and 600 grams of flour, which as a ratio would be 6 to 1800 to 600. Now, if we want a third of the original number of pancakes, and let's remind ourselves of the original quantities. To make 12 pancakes, it was 3 eggs, 900 millilitres of milk, and 300 grams of flour, and the ratio was 3 to 900 to 300. Well, with 1/3 of the original quantities, we will get 1/3 of the number of pancakes. So we'll have 1 instead of 3, 300 instead of 900, and 100 instead of 300. So instead of our original 12 pancakes, we will actually make 4 pancakes. Remembering, of course, as long as we keep the relative proportions of each ingredient the same, our recipe still works.
But looking at it the other way round, suppose we've got 24 pancakes and we need to divide them between 3 people, but in the ratio 1 to 2 to 3. How would this work?
Suppose the people are called Jim, Alan and Jane, and we wish to share the pancakes between them in the ratio of 1 to 2 to 3. The total number of parts is 1 plus 2 plus 3, which is 6. So 6 parts represent 24 pancakes. Now, how many pancakes does each part represent? 24 divided by 6 gives us 4. So 4 pancakes represent 1 part. Now, if we share the pancakes between Jim, Alan and Jane in the ratio of 1 to 2 to 3, that means Jim, with 1 part, will get 4 times 1, or 4 pancakes. Alan, with 2 parts, will get 2 times 4, or 8 pancakes. And Jane, with 3 parts, will get 3 times 4, or 12 pancakes. Remembering, of course, that the ratio of 4 to 8 to 12 is the same as a ratio of 1 to 2 to 3.
Right, now that I've got my tea sorted, let's go to a question. The sort you might find in your test. There are 2 parts to this question, so you might find it handy to jot them down. You can make different colours of paint by mixing red, blue and yellow in different proportions. For example, you can make green by mixing 1 part blue to 1 part yellow. Part A. To make purple, you mix 3 parts red to 7 parts blue. How much of each colour do you need to make 20 litres of purple paint? And give your answer in litres. Part B. To make orange, you mix 13 parts yellow to 7 parts red. How much of each colour do you need to make 10 litres of orange paint? And give your answer in litres. Right, how did you get on? Let's work through the answers with the lead chief marker. Part A first.
How much of each colour do you need to make 20 litres of purple paint? And the question tells us to give our answer in litres. To make purple paint, we need to mix 3 parts red and 7 parts blue. We could write this as red to blue, 3 to 7. And we are asked how much of each colour we need to make 20 litres of purple paint. Well, as the question has told us the units we are dealing in, litres, let's assume it is 3 litres to 7 litres. 3 litres of red and 7 litres of blue, that makes 3 plus 7, 10 litres of purple paint altogether. But we want to make 20 litres of purple paint. That's twice the amount. So we must need twice the amount of red and twice the amount of blue. That's 3 multiplied by 2, 6 litres of red, and 7 multiplied by 2, that's 14 litres of blue, to make 20 litres of purple paint.
Great. Now, what about part B and the orange paint?
How much of each colour do you need to make 10 litres of orange paint? And again, we need to give our answer in litres. Let's write the proportions of paint as a ratio again. So we have 13 parts yellow to 7 parts red this time. That's yellow to red, 13 to 7. And this time we're asked how much of each colour we need to make 10 litres of orange paint. Again, the question has told us the units we are dealing in, litres. So let's assume it is 13 litres to 7 litres. 13 litres of yellow and 7 litres of red. That's 13 plus 7, 20 litres of orange paint altogether. But we are looking for 10 litres of orange paint. That's half the amount. So we must need to divide the amount of yellow by 2 and divide the amount of red by 2. That's 13 divided by 2, 6.5 litres of yellow. And 7 divided by 2, that's 3.5 litres of red, altogether to make 10 litres of orange paint as required.
I think a ratio is a fraction or a proportion of a whole.
Ratios are used to describe fractions. If a boy's height was 4 to 5 of his father's, it would be 4/5 of his height.
Ratios are used to describe a fraction, and if you double or triple one side, you have to double and triple the other side.
A ratio gives a comparison between two or more quantities. It shows us how many times bigger one quantity is in comparison to another. The actual quantities or units in a ratio don't matter, but the proportions have to be kept the same. That's it for this unit. There are more examples and questions in the book and also on the website. You may also want to rewind and recap on some of those calculations, or you might feel the need to take a break before moving on. This unit on graphs is divided into three sections, one on coordinates, one on mappings, and another on straight line graphs. Let's begin with coordinates. Now, coordinates are very useful for pinpointing a particular spot. If I draw a point here, for example, how could I explain exactly where that point X is? Well, that's where coordinates come in useful. Take an example of this tourist trying to get from one part of London to another. Now, she's trying to find Covent Garden in London. She knows it's on this page of her map in square J7. So she finds column J and row 7, and where she's trying to get to is Covent Garden. So any square on the map can be located by using the numbers and letters on the grid. The letter and number pair J7 is called the coordinate of the square, and it tells us exactly where it is on the page. We can do the same with a graph, like this. We can find the coordinate of any point by using the x-axis that goes across the graph horizontally, remember x is across, and the y-axis that goes up and down the graph vertically. All points are measured from this point here, where the x and the y-axis meet, also called the origin. This point here would be 2 along and 1 up, or 2, 1. This point here would be 4 along and 3 up, or 4, 3. For more, here's the expert.
Let's find a point on the graph, 4, 3. First of all, you start with the x-coordinate, so we go along to 4, and then you find the y-coordinate, so we go up to 3, which brings us to this point here. Let's label it 4, 3. When you do that, you open a bracket, you write the x-coordinate first, then you put a comma, and then you write the y-coordinate, and you close the bracket. The order you do this is very important. Let's look at another point with similar numbers but the other way round. Let's look at 3, 4. 3 along on the x-axis and then 4 up, which brings us to this point here. And remembering when you write down coordinates, you write the x-coordinate first, 3, and then the comma, and then 4, and then we close the bracket. As you can see, 3, 4 is a very different point to 4, 3.
But this is only 1/4 or quadrant of a much bigger graph, and we can use coordinates to specify points in any of those 4 quadrants. In the first quadrant, the numbers along the x-axis and the y-axis are positive, so all the points in this quadrant have positive x and y values, like 4, 3. If we go down to the next quadrant, all the points in here have positive x numbers but negative y numbers, like 4, -3. And if we go into this quadrant, then points here have both negative x values and negative y values, like -4, -3. And finally, in this quadrant, we have negative x and positive y values, like -4, 3. So all 4 quadrants of the graph would look like this. OK, armed with that information, let's go for a test question. Daniel has some parallelogram tiles. He puts them on a grid in a continuing pattern. He numbers each tile. The diagram shows part of the pattern of tiles on the grid. Daniel marks the top right corner of each tile with a circle. Part A asks, what are the coordinates of the corner with a circle on tile number 2? Part B asks, what are the coordinates of the corner with a circle on tile number 4? Finally, Part C says, Daniel marks the bottom right corner of each tile with a cross. Fill in the table to show the coordinates of each corner with a cross. So, time to stop the tape and have a go at that. OK, now for the answers. Let's go to the lead chief marker for Key Stage 3 Maths.
This question is about coordinates, so I'll go through it step by step. The question says that Daniel has some parallelogram tiles and puts them on a grid in a continuing pattern. The diagram shows part of the pattern of tiles on the grid. Daniel marks the top right corner of each tile with a circle. Part A asks, what are the coordinates of the corner with a circle on tile number 2? That's this point here. Starting at the origin, we move across first. 4 across and up 4. So that's the point 4, 4.
Part B?
Part B asks, what are the coordinates of the corner with a circle on tile number 4? We can see the coordinates of the corner with a circle on tile number 1 is 2, 2. On tile number 2, we worked it out to be 4, 4. And on tile number 3, it is 6, 6. So we might expect the corner for tile number 4 to have coordinates twice the tile number 2. That's 8, 8. But let's just check by extending the diagram a little. This is where the coordinates of the corner with a circle on tile number 4 would be. And starting at the origin, we move across first, 8 across right and up 8. So that is the point 8, 8.
Part C.
Finally, Part C says, Daniel marks the bottom right-hand corner of each tile with a cross. Fill in the table to show the coordinates of each corner with a cross. We're given the coordinates of each corner marked with cross for tile 1, that's here. Starting at the origin, we move across first, 2 across right, and up 1. So that is the point 2, 1. Then for tile 2, the corner marked with a cross is here. That's starting at the origin, across 4, up 3, so that has coordinates 4, 3. Then for tile number 3, the corner marked with a cross is here. Starting at the origin, across 6 and up 5, so that has coordinates 6, 5. And finally for tile 4, we can look at the pattern in the x-coordinates so far. That's 2, 4, 6. So we would expect tile 4 to continue adding 2 and have x-coordinate 8. And we can also look at the pattern in the y-coordinates so far. That's 1, 3, 5. So we would expect tile 4 to continue adding 2 again and have y-coordinate 7. Let's just check though by extending the diagram. The corner marked with a cross for tile 4 would be here, and starting at the origin, across 8 and up 7, that's coordinates 8, 7.
Let's go to the key points about coordinates. The x-axis goes across horizontally. The y-axis goes up and down vertically. Coordinates are written with an x value first and then the y value. When plotting or reading points, count from the origin, which is 0, 0. Move to the right for positive x values, move to the left for negative x values. Move up for positive y values and move down for negative y values. And when plotting, make sure that your pencil is sharp so that the exact point that your cross marks is absolutely clear. Now onto mappings. Mappings are diagrams that show a rule that you apply to one number to give another number. They may be used to give us coordinates of points. In this example, we say these values map onto one another. So 2 maps to 1. 1 maps to 0. 0 maps to negative or minus 1. Negative 1 maps to negative 2. And negative 2 maps to negative 3. So in other words, for each arrow, we subtract 1 to take us to the new value. So the rule of this mapping is to subtract 1. If we were to write this down in table form for the x and corresponding y-axis, it would look something like this. So when x is 2, y is 1. When x is 1, y is 0. When x is 0, y is minus 1, and so on. In fact, we can write this as an equation, y equals x minus 1, and we can plot our coordinates to give us the graph of this equation. Let's look at another example. Take this mapping diagram, or this table, showing the values of x and y. When x is 2, y is 5. When x is 1, y is 4. When x is 0, y is 3, and so on. The relationship between x and y is such that y is always the x value plus 3. We can plot our coordinates to give us the graph of this equation. Let's move on to straight line graphs. Do you remember the unit on algebra and equations in Programme 2? Well, another way to represent an algebraic equation is to draw it on a graph. For instance, some students at this school have set up a small internet cafe during lunch times and after school. They charge £1 to join and then £2 for every session spent on the internet. In other words, the £1 fee is fixed and the rest of the cost depends on the number of sessions the students go to. And at £2, it's twice the number of sessions attended. The students can work out the total charges using an equation. Let's go to our expert for more information.
The total cost in pounds for each student equals £2 for each session attended, so £2 times the number of sessions plus a fixed joining fee. Now the cost of that joining fee is £1. Right, so if we use y to represent the total cost and x to represent the number of sessions, then the total cost equals y, which equals 2 times x plus 1. And we can also write that like this: y equals 2x plus 1. There are several ways in which we can represent this equation in order to plot the points as a graph. We can use mapping. The x values are put into a column, and these are mapped onto y values according to the equation. So taking the first value, x equals 1, 2 times 1 plus 1 gives us a value of 3. So x equals 1 maps onto y equals 3. Taking the second value, x equals 2, 2 times 2 plus 1 gives us 5. So 2 maps onto 5, and so on. Now, another way we can represent this equation is in the form of a table. The number of sessions, x, and the total charge in pounds of y. So, remembering to use the equation, the value of 1 for x, 2 times 1 plus 1 gives a total charge of £3 for one session. The value x of 2, using the equation, 2 times 2 plus 1, gives a total charge of £5 for those sessions. All of these values can be plotted as coordinates on a graph. Okay, the first coordinate, 1, 3, is located here, 1 on the x and up to 3 on the y. Let's mark that point and label it. Bracket 1, 3, close bracket. The second point, 2, 5. 2 on the x coordinate and 5 coming up to 5 on the y coordinate. Let's mark it and label it. Bracket 2, 5, close bracket. And the third point, 3, 7. 3 on the x and up to 7. That brings us here. Mark it, open bracket, 3, 7, close bracket. Now we can join these points as a straight line. And the intersection of these points is here at 1, which corresponds to the plus 1 in this equation. Right, now you can use any value of x that you want to calculate the corresponding value for y in the formula. We just happen to use these particular ones. But when you do your calculations for the graph, you should notice if you plot 2 points, it should give you a straight line. But you should do a third as a check. And if you don't get a straight line, then what you should do is recheck your calculations.
Let's take it a bit further.
If we consider the equation y equals 2x plus 1, we can draw it like this. And you'll see that the intersection with the y-axis is here, where y equals 1. And that corresponds to plus 1 in the equation. If we look at this equation, y equals 2x plus 4, if we draw it, it will look like this. Now here we can see that this line is parallel to the first line, but the intersection here with the y-axis is at 4, and that corresponds to plus 4 in the equation. Right, the last equation we'll look at is y equals 2x minus 2. And if we draw this equation, it will look like this. And here again, it's parallel to the first two, and the intersection with the y-axis is at minus 2. And that corresponds to minus 2 in the equation.
Let's look at another equation.
Let's consider the equation x equals 4. If we want to represent this as a graph, we need coordinate pairs. So, let's start with y equals 0. Y equals 0 and x equals 4. Let's draw that in. When we label it, open brackets, x-axis 4, comma, and then a 0. And we close the brackets. Let's consider another point. When y equals 2, x still equals 4. So if we plot that point, we come here. Let's label that. Remember, x coordinate is written first, 4, comma, 2. And one more point. When y is 4, x is still 4. And that brings us to this point, which is here. And when we label that, x coordinate first, 4, comma, 4, close bracket. So let's draw the line. So this vertical line is the graph of the equation x equals 4. Let's consider another example, the equation y equals minus 1. We can represent this as a graph by drawing coordinate points. Okay, if we consider where x equals 0, that's here, y will equal minus 1. So let's mark this point and label it. Open brackets, x coordinate first, 0, comma, minus 1, close brackets. Okay, let's look at another point. Let's consider x equals 2. Right, x equals 2 is here, y still equals minus 1. That brings us to this point. Let's mark it and label it. Open brackets, x coordinate first, 2, comma, minus 1, and close brackets. We can join these points with a line. In fact, whatever value of x we use, y is always minus 1.
Okay, now let's summarise. To plot the graph of an equation, work out the coordinates of various points by mapping x values to y values, or writing corresponding pairs of x and y values in a table. To draw a straight line graph, work out 2 points which join up to create the straight line, and then a third point that should be on the line to check that you've drawn the line correctly. The equation of a straight line graph is written with a y value equal to an x term followed by a number. The number tells us where the graph crosses the y-axis. So the straight line graph of y equals 3x plus 2 crosses the y-axis at 0, 2. Equations of straight line graphs with the same x term but with different numbers cross the y-axis at different points, but the lines are parallel to each other. So the graphs of y equals 3x, y equals 3x plus 1 and y equals 3x plus 2 are parallel to each other because they all have the same x term, 3x. Okay, now for an exam question. There are 3 parts of this to jot down. The question begins by telling us to look at this diagram. Then part A tells us that the line through points A and F has the equation y equals 11 and asks what is the equation of the line through points A and B. Part B says the line through points A and D has the equation y equals x plus 3. What is the equation of the line through points F and E? Finally, part C asks, what is the equation of the line through points B and C? Have a go yourself and then play on to see how you got on. Over to the marker for the full answer.
This question is all about the relationship between equations and their graphs, so I'll go through it step by step. Part A begins by telling us that the line through points A and F has the equation y equals 11. We know that because whatever point we look at on that line, its y-coordinate is always 11. Now the question asks us for the equation of the line through points A and B. Now we can see that whatever point we look at on this line, it has an x-coordinate of 8. So we can call this line x equals 8. Part B begins by telling us that the line through A and D has the equation y equals x plus 3, and asks what the equation of the line through F and E is. We can see that the line through F and E is parallel to the line through A and D, which is y equals x plus 3, so the line through F and E must have the same x term. So we know its equation is y equals x plus something. Now we can see that the line through A and D, which is y equals x plus 3, crosses the y-axis at the point 0, 3. So the line through E and F, which crosses the y-axis at the point 0, 7, must have the equation y equals x plus 7. Part C asks, what is the equation of the line through points B and C? Again, we can see that the line through B and C is parallel to the line through A and D. So again we know it has the same x term. So it could be y equals x plus something. This time we can't see where the line crosses the y-axis. So let's extend it until it does. It crosses the y-axis at the point 0, minus 1. The line through B and C therefore has the equation y equals x minus 1.
Okay, we've seen how we can use graphs to represent algebraic equations. Now, for another use of straight line graphs, cast your mind back to the unit on unitary method when we looked at converting between currencies.
Here at the airport, it's all happening, and just here has got to be one of the most important locations on the airport site. It's the Bureau de Change. This is the money exchange where you change your British money, your sterling, into the currency of the country, whichever one it is you're visiting. In my case, could I have £100 in pesetas, please?
Certainly.
Right, so you've got, let's see, pesetas if you're going to Spain, you've got francs if you're going to France, Germany, you've got Deutschmarks, Japan, you've got yen, and America, you've got dollars.
20,000 pesetas.
Tremendous. Thank you very much
1,
indeed. You know,
2,
I
3,
love
4,
this bit.
5, 6,
this is just
7,
great. You get
8,
your hands
9,
on a
10,
great
12,
wad
13, 14, 15,
of
16,
interesting
17,
looking
18,
notes.
19, 20,000. Good.
Thank you very much indeed, sir.
Okay.
Look at that. The thing is, I don't really know exactly how much all this is worth, but Andy Williams knows. He works with foreign money every day. Andy, what's people's reaction usually when they get a great wad of money like this?
Normally they think they're rich because they're still thinking English when they're changing their money. So for 20,000 pesetas, they think it's £20,000, and they obviously think they're rich.
So, what currencies do you exchange most of?
Pesetas, dollars, Italian lira, and Greek drachma.
All right, so people are going to Spain, they're going to, what do you say, pesetas, lira, Italy, drachmas, Greece,
Right,
and American
yes.
dollars. All right, let's go and find out if people know what the peseta in their pocket's actually worth. Where are you flying to today?
Canary Islands.
Okay, what's the currency in the Canary Islands?
Pesetas.
Pesetas, all right. It's a nice T-shirt, good T-shirt. You buy that, perhaps?
Yeah, maybe.
Yeah? Okay, 15 quid that T-shirt would cost in this country. I'd sell it to you for 4,000 pesetas. Now, is that a good deal or isn't it?
Yeah, it's a good deal.
I'm afraid it's not a good deal because it's about 200 pesetas to the pound. So really, you're paying 20 quid for something that's 15 quid. Excuse me, can I ask you a couple of questions?
Yeah.
Where are you travelling to today?
Portugal.
Portugal, okay. Have you exchanged your money yet?
Yes.
Good, all right. Well, you should know what we're talking about. Okay, this T-shirt, I would sell to you for about £15 in this country.
Right.
Now, if I were to offer it to you for 2,000 escudos, is that a good deal?
Yes.
Yes.
It is. Okay, how much is that? Do you realise?
About
It's about...
£6 or £8.
It is. It's £8. How did you work it out?
Because I think it's 250 escudos per pound. I think.
That's absolutely right. Excuse me, can I ask you where you're flying to today?
Verona
In Italy.
in Italy.
All right, so that's lira. Well,
Yes.
consider this T-shirt for a moment, right? Now, that would be about £15 in this country. If I offered to sell that to you for 36,000 lira, is that a good deal or a bad deal?
36. That's slightly dearer than in England.
Ever so slightly dear.
Yes, slightly.
It's pretty close, actually.
Yeah, so it's slightly dearer.
So it's about the same price.
Yes.
So would you buy it anyway?
No, not for that
No.
price.
Everybody has their own way of working out their holiday money. I personally prefer to use this money changer. But if it doesn't grab you, here's a Massphere's special patent currency converter. Up this side of the graph, we've got pesetas. And along the bottom of the graph, we put the pounds. Now today, I got 196 pesetas to the pound, and I changed £10, giving me 1,960 pesetas. We'll put a cross where the two lines meet and draw a line back to the origin, or zero. Now you can work out any price up to £10 by reading across from the side and down to the bottom. So if this roll of film was priced at 689 pesetas, we can see that it's going to cost the equivalent of about £3.50. You can make one of these graphs for any foreign currency. What you need to do is remember how much British money you've changed and how much foreign currency you got for it. So if you were going to Greece and changed £20, you would get around 7,300 drachmas. Use the squares on the graph to make a convenient scale. Mark a cross where the two lines meet and draw a line back to the origin. So you can see something costing 2,000 drachmas is just under £5.50.
To take it a bit further, let's go to our expert.
If you remember in the first programme, we were talking about converting between pounds and euros. And I wanted to know how many euros I would get for £100. Well, if we consider a currency rate of £1 gives 1.5 euros, well then if I have £100, I will have 100 times that amount of euros. So the answer then is £100 equals 150 euros. Let's consider other values. The answer then is to draw a conversion graph. We have pounds here on the y-axis, and we have euros on the x-axis. We could have drawn this the other way round, but we've just chosen to do it this way. Right, let's plot the points that we know. We have £100 equals 150 euros. So we find £100 here, and then we find 150 euros, which brings us to this point here. So we know another point where £0 is 0 euros, which is this point here. So let's connect these points with a straight line using a ruler. We can check if we've done this correctly by looking at another value. So for £10, which is here, it should be 15 euros, and yes, we've done that correctly. We can use this graph to calculate how many euros we will get for £70. £70 is here, which gives us €105. £70 is 105 euros. We can do this the other way round. We can find how many pounds we get for 70 euros. Okay, this time starting on the x-axis, 70 euros is here. Gives a value in pounds of £47. 70 euros equals £47.
We've covered a lot about graphs, so if you don't completely understand it, you can always rewind the tape and look at some of it again. Otherwise, if you'd like to try out more practice questions, then log on to our website or look at the Key Stage 3 Bitesize book. But whatever you do, don't forget to take a break. See you soon. Let's move on to handling data. To start with, collecting and representing data. We're going to look at tally charts, frequency distribution tables, and bar graphs. Now, I'm a fan of basketball and I'm very keen on my local team. Suppose I got hold of some data about how they scored over a range of matches and how some of the individual players in the team performed over the season. Then this would be called raw data. To begin sorting out data, we could use a tally chart. Take a look at this. We're going to concentrate on the scores of 40 different players who have played for this club during the last season. Their scores range from 0 to 43. Now, although we can list the scores individually, it would make a very large table. So to make more sense of it, we can bunch the data up into groups. The first group would include scores of 0, 1, 2, 3 and 4. The next group would have 5, 6, 7, 8 and 9. The third group would be from 10 to 14, and so on until we end up with 9 groups. Take the first score of 32. Now that falls into the 30 to 34 group, so if we were to make up a tally chart, we'd give the 30 to 34 group a tally count of 1. Then the next score of 11. That would fall under the 10 to 14 group, and that would also get a tally count of 1. 34 would also come under the 30 to 34 group, so that now gets a tally count of 2, and eventually we'd end up with a chart like this. So, taking the 0 to 4 group, it has a tally count of 1, 2, 3, 4, cross for 5, 6 and 7. So that means that scores between 0 and 4 have occurred 7 times, or that this group has a frequency of 7. If we did this for all the groups, then we'd end up with a frequency distribution table, like this. Looking at tallies or figures in a frequency table is all very well, but often it's easier to see patterns or trends by looking at a diagram, like a bar chart. A bar chart is a graph with 2 axes. The items in the survey are listed on one axis, and the frequency with which they occur is on the other axis. The actual frequency of each item is represented by the height of each bar. Translating the information from our frequency distribution table, we represent the groups of data on the x-axis, in this case the scores of the 40 players in different groups, and the y-axis shows the frequency or the number of times that scores have occurred. From the tally chart, we know the group 0 to 4 has a frequency of 7, so the height of that bar is 7. The groups from 5 to 9 and 10 to 14 have frequencies of 3, so these bars go up to 3 on the y-axis. The group from 15 to 19 goes up to 8 because its frequency is 8. Notice that the heights of the bars may vary, but the width remains the same, because in bar charts, the intervals are regular. Okay, let's summarise what we've learnt so far. Raw data can be represented in a tally chart. Data can be grouped together so that it's more conveniently represented. A frequency distribution chart is a table which shows the number of times events have happened. The frequency of each item is represented by the height or length of the bar. On a bar chart, frequency is always represented on the vertical axis. Label the axes and give any units. Always remember to give your bar chart a title. You'll lose marks if you don't. Right, it's time for a test question. There are 3 parts to this one, so you might like to jot them down as we go on. Jerry was doing a survey on the use of the new school gym. She asked each of her classmates how many times they had used the gym in the past month. Look at this bar chart showing the results of the survey. Part A asks, how many students are in Jerry's class? Part B asks, how many of Jerry's classmates used the school gym more than 5 times? Part C says, Jill looks at the bar chart and says, all of Jerry's classmates used the gym at least once. Explain why the bar chart does not tell Jill this information. Let's take a look at the answers with the lead chief marker.
As with any question where we have a diagram, let's take a little time to try and make sense of it. Along the x-axis, we have the number of visits to the school gym, and along the y-axis, we have the frequency. So we can see that 12 of Jerry's classmates either didn't use the gym at all or used it only once. 5 classmates used the gym 2 or 3 times, 8 used the school gym 4 or 5 times, 3 used the school gym 6 or 7 times, and 2 used it 8 or 9 times. Now, the first question, part A, asks how many students there are in Jerry's class. So we need to add together the heights of each of the bars. That's 12 plus 5 plus 8 plus 3 plus 2, which is 30 in total. Part B asks, how many of Jerry's classmates use the school gym more than 5 times? So we need to look at the number of students who use the school gym 6, 7, 8 or 9 times. So that's 3 plus 2, which is 5. Finally, Part C says, Jill looks at Jerry's bar chart and says all of Jerry's classmates have used the school gym at least once. Explain why the bar chart does not tell Jill this information. Well, Jill says all of Jerry's classmates have used the school gym at least once. That means once or more than once. But the first bar shows that 12 of Jerry's classmates did not use the gym at all or only used it once. But we cannot tell how many of those 12 used it no times and how many used it exactly once. So Jill could be wrong, since we don't know if all of Jerry's classmates have used the school gym at least once.
Now on to pie charts. A survey was carried out in this large boys' school. It looked at the favourite sports of a class of 32 pupils and found the top 4 activities were baseball, cricket, short tennis and running. The survey shows that 8 pupils preferred baseball, 4 preferred cricket, 4 preferred running and 16 preferred tennis. Looking at the number of pupils who preferred each sport as a fraction of the entire class, then we can see that baseball represents 8 out of the 32 pupils, cricket 4 out of 32, running 4 out of 32 and tennis 16 out of 32. We can then simplify or cancel these fractions and show that a quarter of the class preferred baseball, an eighth preferred cricket, an eighth preferred running, and half of the class preferred tennis. Now, if we want to see this data as a diagram, we could represent these proportions on a pie chart. Now, this is exactly as it sounds. It's a chart in the shape of a pie. So if we divide the pie up according to the different proportions, it will look like this. Each sector represents a specific piece of data. So working clockwise, we can see that 1/4 of the class's favourite sport is baseball, and that takes up a quarter of the circle. Then 1/8 prefer cricket, another 8 prefer running, represented by these 2 sectors. And finally, the fraction of pupils who preferred tennis is 1/2, shown by the final segment. Notice that all the fractions represented by a pie chart add up to 1/2 of a circle. It's time for another test question. There are 3 parts to this one, so you might like to jot them down as we go on. These pie charts show some information about the ages of people in Greece and in Ireland. There are about 10 million people in Greece and there are about 3.5 million people in Ireland. Part A says, roughly what percentage of people in Greece are aged 40 to 59? Part B, Dowie says the charts show that there are more people under 15 in Ireland than in Greece. Dowie is wrong. Explain why the charts do not show this. Part C says, there are about 60 million people in the UK. The table shows roughly what percentage of people in the UK are of different ages. Draw a pie chart below to show the information in the table. Label each section of your pie chart clearly with the ages. OK, now for the answers with the lead chief marker.
Part A says, roughly what percentage of people in Greece are aged 40 to 59. So we need to look at the pie chart headed Greece and look at the 40 to 59-year-old sector. This sector is about a quarter of the pie chart, that's 25%. So roughly 25% of the people in Greece are aged 40 to 59. Dowie says the chart shows there are more people under 15 in Ireland than in Greece. Explain why the charts do not show this. First look at the pie chart headed Ireland. The sector of pie representing the proportion of people in Ireland under 15 is about a quarter or 25%. But that's 1/4 or 25% of the total population of Ireland, which is 3.5 million people. We know that a quarter of 3.6 million people would be 0.9 million. So a quarter of 3.5 million is just under 0.9 million. Now let's look at the pie chart headed Greece. The sector of pie representing the proportion of people in Greece under 15 is about 1/5 or 20%. That's 1/5 or 20% of the total population. That's 10 million people. A fifth of 10 million is 2 million. That means there are actually fewer people under 15 in Ireland than in Greece. Dowie made the mistake of looking at the actual sizes of the sectors of pie instead of looking at the numbers they represented.
Now, part C.
The pie chart is already divided into 10 equal sectors. So each sector of the pie chart represents 1/10 or 10% of the number of people in the UK. The table tells us that 20% of the people in the UK are under 15. So we must label two sectors of 10% as representing people under 15. Next, the table tells us that 35% of the people in the UK are 15 to 39-year-olds. So we must label 10, 20, 30% and another 5%, that's another half a sector, to represent 15 to 39-year-olds. Next, the table tells us that 25% of the people in the UK are 40 to 59-year-olds. So that's 10%, 20% and another half a sector for the 25% that are 40 to 59-year-olds. And these final two sectors represent the 20% that are over 59 years old.
Let's just summarise by taking a look at some key facts about pie charts. A pie chart is a circular diagram which looks like a pie, divided into portions. Each portion of a pie chart is called a sector. Each sector represents a fraction of a whole. Let's move on. Line graphs show us how data changes over intervals of time or distance. If a straight line can be drawn through all the points plotted, we say that the relationship is linear. If the line curves, the relationship is said to be non-linear. There can be more than one line on the graph, so make sure you refer to the key to see what the lines represent. For example, these graphs show the depth of water as containers fill up. Let's look at graph 1. At 2 seconds on the x-axis, the container has filled to a depth of 5 centimetres. When the same amount of time has passed again, at 4 seconds, then it's filled to the depth of 8 centimetres. And the same amount of time again, it's filled to a depth of 9. So although the same amount of time passes on each occasion, the water in the container fills at a slower and slower rate. This could be because the container is getting wider. Now look at graph 2. At 2 seconds on the x-axis, the container has filled to a depth of 3 centimetres. In another 2 seconds, it's filled to nearly 5. In the same time again, to a depth of just over 5. And in a further 2 seconds, to a depth of 7 centimetres. With this graph, although the amount of time passing is the same, the depth of the water seems to be slowing down first of all, and then gets faster again. This could be because the container is wider and then thinner, like a goldfish bowl. Remember, a line graph is always trying to illustrate a relationship. You just have to work out what it is. Okay, time for a test question. A child is having a bath. The simplified graph shows the depth of water in the bath. Part A. From A to B, both taps are turned full on. What might be happening at point B? B. Which part of the graph shows the child getting into the bath? Let's see how you got on. Here's the lead chief marker to take us through the answers.
Let's begin by just taking a moment to look at the graph and make sense of the story it's telling us. The x-axis is labelled time. The y-axis is labelled depth of water. So the graph shows us how the depth of water changes over time. So here, from A to B, we can see that the depth of water is increasing at a steady rate. Then, from B to C, the depth is still increasing, but at a slower rate. From C to D, the depth stays the same, until from D to E we see a sudden rise in the depth. From E to F, the depth of water stays the same again. From F to G, there is a steady decrease in the depth of water, then a faster decrease from G to H, and a slower, steady decrease from H to I.
So, how about the answer to part A?
Part A of the question tells us that from A to B, both taps are turned full on, which explains the steady rate of increase in the depth of water. Then we're asked what might be happening at point B. Well, at point B, the depth of water is still increasing, but at a slower rate. There are several possible explanations for this. For instance, one tap may have been turned off completely, or both taps may have been turned down. Part B asks which part of the graph shows the child getting into the bath. That will be where there is a sudden rise in the depth of water, which is from D to E.
Okay, now to summarise. Line graphs show how data changes over intervals. Line graphs that connect data by a straight line are said to show a linear relationship. Line graphs that connect data by a curved line are said to show a non-linear relationship. There may be more than one line graph on a pair of axes. This is the end of the unit on collecting and representing data. Now, don't forget, whenever you see data represented in a table or in any kind of chart, graph or diagram, take a little time to make sense of it before doing anything with it or answering any questions about it. And if there's anything you don't understand about the mathematics in this unit, then you can always rewind the tape and play it again. There's also more information and exercises in the book and also on our website. But before you move on, why don't you take a break? So, now we've seen how to represent different types of data, let's move on to comparing data. First, scatter diagrams. Scatter diagrams allow you to compare sets of data or distributions by looking at the pattern of plotted points. Look at these people enjoying lunch at this restaurant. In fact, there are two areas of the restaurant, an indoor one and an outdoor one. The manager needs to organise his staff rota for the summer weekends and bank holidays when the restaurant gets very busy. He wonders if on hot days he should put his waiters and waitresses in charge of more tables in the outdoor area of the restaurant than in the indoor area of the restaurant, or whether even if it's hot, people prefer to eat inside in the shade. The manager asked one of his staff to collect some data to help him out. First, the outdoor restaurant. Now, look at these scatter diagrams drawn by one of the waitresses and see if we can make sense of them. As a starter, it's always a good idea to read the description or title. This one says the scatter diagram shows the temperature at midday in degrees centigrade and the number of people at midday in the outdoor area of the restaurant for weekends and bank holidays in April and May. Let's see if there's any relationship between the varying temperature and the varying number of people outdoors. Look at the pattern of points plotted. You can see that as the temperature increases, the number of people using the outdoor area of the restaurant increases. When one variable increases as another increases, we say that there is a positive relationship or a positive correlation between them. Now, the indoor restaurant. The other scatter diagram shows the midday temperatures and the midday number of people in the indoor area of the restaurant on weekends and bank holidays in April and May. Let's see if there's also a relationship between the varying temperature and the varying number of people in this area of the restaurant. Looking at the pattern of points plotted, you can see that this time, as the temperature increases, the number of people using the indoor area of the restaurant decreases. When one variable increases as another decreases like this, we say that there is a negative relationship or a negative correlation. If we draw a straight line through the points on this scatter diagram, with as many points as possible on the line and roughly the same amount of points that aren't on the line lying either side of it, then we get what we call the line of best fit. We can use this line of best fit to make some estimations. When the temperature is 16 degrees centigrade at midday, we can estimate that there will be 10 people in the indoor area of the restaurant. And when the temperature is 21 degrees, then we can estimate there'll be 4 people in the indoor area of the restaurant. Now, the waitress also did a count of people in the indoor and the outdoor areas of the restaurant at 6 p.m. Let's look at that data and see if it tells us a different story. This scatter diagram shows the 6 p.m. temperatures and the 6 p.m. count of the number of people in the indoor restaurant on weekends and bank holidays in April and May. Notice that there does not really seem to be a pattern of plotted points. So here we say that there appears to be no relationship or no correlation. Okay, let's summarise. If the plotted points of a scatter diagram show that values in one data set increase as the values in another increase, then there is said to be a positive correlation. Conversely, if the values in one data set increase as the values in another decrease, then we say that there is a negative correlation. If the plotted points show no pattern at all, then we say that there is no correlation. A line of best fit is a straight line drawn through the middle of the points on a scatter diagram, as close to as many points as possible. It can be used to make estimations about the data. Okay, time for a test question. There are 3 parts to this, so you may want to jot them down. The scatter diagram shows the heights and masses of some horses. The scatter diagram also shows a line of best fit. Part A. What does the scatter diagram show about the relationship between the height and the mass of horses? Part B. The height of a horse is 163 centimetres. Use the line of best fit to estimate the mass of the horse. Part C. A teacher asks his class to investigate this statement. The length of the back leg of a horse is always less than the length of the front leg of a horse. What might a scatter graph look like if this statement is correct? Use the axes below to show your answer. OK, now for the answer with the lead chief marker.
What does the scatter diagram show about the relationship between the height and mass of horses? We can see from the plotted points that as the heights of the horses increase, so do their masses, and the upward slope from left to right of the line of best fit confirms this. Therefore, we can say that there is a positive relationship or positive correlation between the height and mass of the horses.
Now, Part B. The height of a horse is 163 centimetres. Use the line of best fit to estimate the mass of the horse.
Look at the height axis, that's the horizontal axis, and read off from this. You can see there are 10 centimetres between 140 centimetres and 150 centimetres, and only 5 squares. So each square along this horizontal axis represents 2 centimetres. So a horse of height 163 centimetres would read here. Let's draw a line up from 163 centimetres to the line of best fit. Now along to the vertical axis that shows the mass of the horse. We can see there are 100 kilograms between 500 kilograms and 600 kilograms and only 4 squares. So each square along this vertical axis represents 25 kilograms. Our line comes to here, which is more than 575 kilograms and less than 600 kilograms. So using our line of best fit, we would probably estimate that a horse of 163 centimetres would have a mass of 590 kilograms.
Part C.
Look at this statement. The length of the back leg of a horse is always less than the length of the front leg of a horse. What might a scatter graph look like if the statement is correct? Use the axes below to show your answer. We have been given axes where the horizontal x-axis is labelled length of front leg in centimetres, and the vertical y-axis is labelled length of back leg in centimetres. We're told that the length of the back leg, that's on our vertical axis, is always less than the length of the front leg, that's on our horizontal axis. So, if the length of the front leg is 70 centimetres, the length of the back leg must be less than that, perhaps 65 centimetres. So we can plot our first point of the scatter diagram here. If the length of the front leg is 80 centimetres, the length of the back leg must be less than that, perhaps 70 centimetres. So we can plot our second point here. If we continue to plot points in this way, our scatter diagram may look like this, or like this, or like this. Notice that in all these scatter diagrams, all the points lay below an imaginary line across here, where the length of the front leg equals the length of the back leg. As long as all the points on your scatter diagram lie below this line, then your answer is correct.
Another way of comparing several sets of data would be to look at averages. An average actually gives a representative value for a whole range of data in a data set or distribution. But there are several types of averages, and they all have different names. Before we go any further, take a look at this. Here we can see Ealing Tornadoes' basketball team. They've played well on some days and not so well on others. Let's suppose that in this season the team has played 6 games. On one occasion they won 60 to 12. On another occasion they won 45 to 12. But in one game they lost 15 to 84. Ealing Tornadoes are hoping to do even better later in the season, and they're hoping to encourage this coach to train them. He's been watching them on several occasions, keeping a close eye on their performances. Now, suppose the coach wants to make sense of the data for the 6 games played so far this season. To find out how strong the team's attack is, he could look at the average number of points that they have scored in the 6 games. To find out how strong their defence is, he could look at the average number of points that they have let in. That's the scores of those teams they've played against in the 6 games. A very common type of average is the mean. To find the mean, we total all the quantities and then divide by the number of quantities that we have. So, if we look at the made-up scores of the Ealing Tornadoes, we add up 28 and 60 and 22 and 28 and 15 and 45, and then divide them by the total number of games. That's 6. This comes to 33. Now, to see how the opponents fared and to learn a bit more about the mean, here's the expert.
So now let's try and work out the mean score for the opponent's team. We've got 28, 12, 26, 12, 84 and 12 again. So we add those up and that gives us a total of 174. We divide that by the number of scores in the list. That's 1, 2, 3, 4, 5, 6. 174 divided by 6 gives us an answer of 29. So the mean score for the opponent's team is 29. Although the mean score was correctly worked out to be 29, that's a little bit deceiving if we look at this chart here. In 5 out of their 6 games, they actually scored less than 29. Victoria Park scored 28, Osney Town scored 12, Perch United scored 26, 12 and 12. Only in one game did they actually score more than 29. So to say that they had an average of 29 is a little bit deceiving. What's happened is that in this game here, where they scored 84, that score has distorted the mean average for the opponents.
So you need to be careful with the mean. If there's a value that is much bigger than the rest or much smaller than the rest, the mean just might misrepresent the data. So it's probably better to use a different average, such as the median or the mode.
The Ealing Tornadoes scored 28, 60, 22, 28, 15 and 45. To find the median average, the first thing we have to do is put all the scores in order of size, starting with the smallest to the largest or largest to the smallest. It doesn't really matter. We're going to order them from smallest to largest. Okay. Once we've done that, we need to find the middle value, the middle of these 6 values here. That falls between the 3rd and the 4th value, 28 and 28, which means the median score is 28. Let's change one of the 28s to a 27. Again, we have to find the middle value of these 6 values here. This time it falls between the 27 and the 28. So the median is halfway between these 2 values. That makes it a median score of 27.5. So let's say that the Ealing Tornadoes played a 7th game and they had a winning score of 63. We'd have to add that to our list here, 63. Now again we want to find the middle value. This time it falls exactly on the 4th value here, 28, right in the middle. Look, we've got 1, 2, 3 less and 1, 2, 3 more. So that gives us a median average of 28.
Finally, let's look at the mode, an average measured by looking for the quantity that occurs most often. In this case, the score that occurs most often. Back to the expert.
So let's look at the modal average for the Ealing Tornadoes, and that's the score that occurred the most often. We can see they scored 28 twice, 60 once, 22 once, 15 once and 45 once. So the score that occurs the most often is 28. Therefore, the modal average for the Ealing Tornadoes is 28. Now let's look at the score for the opponents of the Ealing Tornadoes. We can see that they scored 28 once, 12, 1, 2, 3 times, 26 once and 84 once. So the score that occurs the most often is 12, and therefore the modal average against the Ealing Tornadoes is 12.
I remembered mode as most, and media is middle. Mean, just know that mean is the average, so you add all together and divide it by how many it is.
I remember mode by thinking that it sounds like most. So if you have some numbers, if 34 was used more than the others, that would be the mode, because it is used the most.
I remember the mean is the average, so you take all of the numbers, add them together and divide it by how many numbers you have.
Median sounds like middle, so if you put the numbers out in order of size, you'd go to the very middle number and that would be your answer.
Let's summarise. An average gives a representative value for all the data in a data set or a distribution. To find the mean, total all the quantities and then divide by the number of quantities that you have. To find the median, place all the quantities in size order and then find the middle one. To find the mode, look for the quantity that occurs most often. Sometimes the mean, median or mode is not enough information on its own. So to back up an average, you might find the range too. Now you can do that by taking the greatest value in a data set and subtract the smallest value. The range shows how spread out the values are, and in this case would show the coach how consistently the team is playing. Here's the teacher.
So let's look at the range of scores for the Ealing Tornadoes. We can see that their highest score was 60 and that their lowest score was 15. So the range is 60 subtract 15, which equals 45. Now let's look at the range of scores for the opponents of the Ealing Tornadoes. Their highest score was 84 and their lowest score was 12. So the range is 84 subtract 12, which equals 72. Now if we take this information of the range being 72, which is a large range, along with the knowledge that the modal average for the opponents of the Ealing Tornadoes is 12, we can see that in general the Ealing Tornadoes do not let their opponents score very highly, but on one occasion they have.
Well, I reckon the team look pretty promising and the coach will give them a chance. OK, a fair amount to take in there. Let's summarise. If there's a quantity in the data set that is a lot bigger than the rest or a lot smaller than the rest, the mean might misrepresent the data. So it may be best to use a different average. Sometimes an average on its own does not give enough information, so we find the range of the data set too. The range measures the spread of quantities in the data set. We find the range by taking the greatest quantity and subtracting the smallest quantity. Now, how about trying a question? This graph shows the range in temperature in Miami each month. For example, in January, the temperature ranges from 17 degrees centigrade to 24 degrees centigrade. Part A asks, in which month does Miami have the smallest range in temperature? Part B says, in July, the range in temperature in Miami is 5 degrees and tells us that there are 5 other months in which the range in temperature is 5 degrees. Then it asks, which 5 months are they? So, how did you get on with the range? Let's have a look at the answers.
The question begins with an explanation of the graph, which says that it shows the range in temperature in Miami each month. Then we are given the example that in January the temperature ranges from 17 degrees, that's here, to 24 degrees, that's here. Now we are asked in which month Miami has the smallest range of temperature. This will be represented by the shortest bar, which appears to be September. where the range is from 26 degrees to 30 degrees. A range of 30 subtract 26, 4 degrees.
Now, part B.
In July, the range and temperature in Miami is 5 degrees. There are 5 other months in which the range and the temperature is 5 degrees. Which months are they? We are looking for months with a temperature range of 5 degrees. We were told that in January the temperature ranges from 17 degrees to 24 degrees. So that is a range of 24 subtract 17, that's 7 degrees. In February we can see the range is bigger than 7 degrees because the bar is even longer than January's bar. In March the temperature ranges from 19 degrees to 25 degrees. So that's a range of 25 subtract 19, which is 6 degrees. Then in April, the temperature ranges from 21 to 27 degrees. So that's a range of 27 subtract 21, which is also 6 degrees. In May, the temperature ranges from 24 to 29 degrees. So that is a range of 29 subtract 24, which is 5 degrees. We found our first month, other than July, with a range in temperature of 5 degrees. In June, the temperature ranges from 25 to 30 degrees. So that's a range of 30 subtract 25, which is also 5 degrees. We were told that July has a temperature range of 5 degrees, so let's move on to August. In August, the temperature ranges from 26 to 32 degrees. So that's a range of 6 degrees. We have already worked out that September had the smallest range of 4 degrees, so let's move on to October. In October, the temperature ranges from 24 to 29 degrees, which is another month with a temperature range of 5 degrees. In November, the temperature ranges from 21 to 26 degrees, yet another month with a temperature range of 5. And finally, December. The temperature ranges from 19 to 24 degrees. 5 degree range again. So the 5 months, other than July, where the range in temperature is 5 degrees, are May, June, October, November and December.
Well, that's it for this unit. There's always more information and exercises in the book and on the website. But if there's anything you'd like to hear again, then just rewind the tape and play it back. Now, the final unit on probability. It's divided into sections on theoretical and experimental probability. Let's start with theoretical probability. Probability is a measure of chance, and we use words like certain, very likely, equally likely, unlikely, and impossible to describe it.
Because I dislike mushrooms, it is almost impossible that I would eat any mushrooms.
The chances of me wearing school uniform to school is certain because they are school regulations.
Because I go on holiday 3 times a year, it is almost certain that I will go on holiday 3 times a year next year.
The chances of me doing my homework is pretty likely because the teachers reward you for doing your homework.
It's almost certain that I wouldn't be a heart surgeon or a nurse or anything to do with blood because I don't like blood.
These words, ranging from impossible to certain, can be put on a scale. Impossible is at one end of the scale, something that cannot ever happen. Certain is at the other end of the scale, something that will definitely happen. Halfway along the scale is equally likely, something which is as likely to happen as not. The words on that scale give us a rough indication of chance, but we can use a much more accurate measure, a number, a probability. Probability is measured as a fraction or a decimal from 0 to 1. So the probability scale now goes from impossible at 0 to certain at 1, with equally likely midway at a half or 0.5. Here's our expert.
Today is Tuesday, so what's the probability of tomorrow being Sunday? Well, we know that Sunday never follows Tuesday, so the probability is 0. The probability of tomorrow being Sunday equals 0. We write that as P brackets tomorrow being Sunday close brackets equals 0. P, the event in brackets, equals 0. On the other hand, what's the probability of tomorrow being Wednesday? That's 1, because Wednesday always follows Tuesday. So we'd write that as P brackets tomorrow being Wednesday close brackets equals 1.
Let's now take a look at a cyclist and work out the probability of some of the turns the cyclist makes. This experienced cyclist is demonstrating to learner drivers some moves that could help them with a forthcoming cycling test. He's approaching a mock-up T-junction. He can turn left or right. Assuming nothing untoward happens and that he can make either turn equally safely, what is the probability that he turns right? Back to our expert.
We can work out the probability of any outcome by dividing the number of favourable outcomes and divide them by the number of total possible outcomes. So if we want to find the probability of a right turn, that's our favourable outcome. So that's the number of right turns, which is 1, divided by the number of total possible turns, which is 2. That gives us a probability of a half, or 0.5.
Now the cyclist is approaching a mock-up crossroads and wants to turn right again, but there are 3 possible outcomes. Right, left, or straight on. So again, assuming that nothing untoward happens and that each direction is equally safe, what is the probability of turning right this time?
This time there is still only one favourable outcome that we want, and that's to turn right. But there are 3 possible outcomes. There's right, left, or straight on. So we take the number of favourable outcomes and divide them by the number of total possible outcomes. In which case we have number of right turns, which is 1, divided by the number of possible turns, which is 3. That would give us a probability of 1/3, or 0.33 recurring.
Now let's look at the scenario where our cyclist approaches a roundabout with 5 exits. Assuming he doesn't want to turn around and come back the way that he came, what is the probability of taking a red exit?
The probability of our cyclist taking a red exit is the number of favourable outcomes divided by the number of total possible outcomes. So that would be the number of red exits, which is 2, divided by the number of possible exits, which is 5. That gives us a probability of 2/5, or 0.4.
But what's the probability of the cyclist not taking a red exit?
The probability of not taking a red exit is the number of exits which are not red, that's 3, divided by the number of possible exits, which is 5. So that's a probability of 3/5. Now if you notice that the probability of taking a red exit is 2/5, plus the probability of not taking a red exit, which is 3/5, adds up to 1 whole. So the probability of an event happening plus the probability of that event not happening equals 1.
Now let's look at how to represent the probability of 2 events happening together, like tossing 2 coins.
With 2 outcomes at the same time, like tossing 2 coins or throwing 2 dice, or tossing 1 coin and throwing 1 dice at the same time, we can record our possible outcomes on a sample space diagram like this one here. So we could have, if we have an example of tossing 2 fair coins, we could have a head and a head, a head and a tail, a tail and a tail, a tail and a head. So there are 4 possible outcomes. Now, if I want to find the probability of getting 2 heads, that would be 1 out of 4. Now, if I want to find the probability of getting a head and a tail, I've got the chance of getting a head and a tail here, that's 1. A tail and a head here. So, The probability of getting a head and a tail, or a tail and a head, is 2 out of 4, and I can reduce that down to a half.
So throwing a head and a tail is twice as likely as throwing 2 heads or 2 tails. But what about a coin and a dice? Similarly, if we throw a fair dice and tossed 1 coin at the same time, the combinations would be a tail and a 1, a tail and a 2, and so on, until a tail and a 6. And a head and a 1, up to a head and a 6. So there are 12 possible outcomes. This means that the chance of throwing, say, a head and a 3 is 1 in 12. 1 divided by 12. Let's summarise what we've just been through. Probability is a measure of chance. It measures how likely or unlikely something is to happen on a scale of 0 to 1. If the probability of an event happening is 0, then it's impossible. If the probability of an event happening is 1, then it is certain. All probabilities are written as fractions or decimals between 0 and 1. The probability that an event is as likely to happen as is not to happen is a half, or 0.5. The probability of an event happening is the number of favourable outcomes we want to happen divided by the total number of possible outcomes. The probability of an event happening plus the probability of that same event not happening is always 1. When dealing with 2 outcomes at the same time, we can show all the possible outcomes on a sample space diagram. Armed with all that, it's time for a test question in 4 parts. I have 2 fair dice. Each of the dice is numbered 1 to 6. A. The probability that I will throw double 6, both dice showing a number 6, is 1/36. What is the probability that I will not throw double 6? Part B. I throw both dice and get double 6. Then I throw the dice again. Tick the box that describes the probability that I will throw double 6 this time. Explain your answer, and it offers a choice of less than 1/36, a 36th, and more than 1/36. I start again and throw both dice. Part C asks, what is the probability that I will throw double 3, both dice showing the number 3? Part D, what is the probability that I will throw a double? It could be double 1 or double 2 or any other double. For the answers, here's the lead chief marker.
This is a typical test question about probability, so I'll go through it step by step. The question says I have 2 fair dice, numbered 1 to 6, and in part A it tells me that the probability I will throw a double 6 is 1/36. It then asks what is the probability I will not throw a double 6. Well, I know the probability of an event happening plus the probability of it not happening always adds up to 1. So if the probability that I will throw a double 6 is 1/36, the probability I will not throw a double 6 must be 1 minus 1/36, which is 35/36. We can check that against the sample space diagram, showing all the possible outcomes when you throw 2 dice, from a 1 and a 1 to a 6 and a 6, double 6. There are 36 possible outcomes in total. There's 1 chance of a double 6 out of 36 possible outcomes, and 35 chances of not throwing a double 6 out of 36 outcomes. That's 35/36 again.
On to part B.
Part B tells me that I throw 1 double 6 and then throw the dice again. it asks me to tick the box that describes the probability I will throw double 6 this time. Less than 1 over 36, 1 over 36, or more than 1 over 36. The fact that I throw a double 6 the first time does not affect the probability of throwing a double 6 the next time. The dice are exactly the same, so the probability will still be 1 over 36.
Part C asks about the probability of throwing a double 3.
Let's use our sample space diagram again. There is one favourable outcome of throwing a double 3, out of a total of 36 possible outcomes. So the probability of throwing a double 3 is 1 over 36. The final part asks, what is the probability that I will throw any double using the 2 dice? Using our probability space diagram, the favourable outcomes of throwing a double are a 1 and a 1, a 2 and a 2, and so on up to a 6 and a 6. That's 6 favourable outcomes out of a total of 36 possible outcomes. So the probability of throwing any double is the number of doubles, 6, divided by the total number of possible throws, 36. 6 divided by 36 simplifies to become 1 divided by 6. That's 1/6.
So, how did you get on? You can always rewind the tape and have another go if you found parts of that question a bit tricky. Now on to experimental probability. What we've just been looking at is theoretical probability. We can work out the number of favourable outcomes and possible outcomes without actually doing anything. We know the probability of getting a head and a tail when tossing a coin. We don't have to toss it. We can work out the probability of throwing a double with 2 dice without actually having to throw them. But there is another way of working out probability called experimental probability, which involves actually conducting an experiment. Take this piece of buttered toast. Now, how do we work out the experimental probability of it landing butter side down? Well, we do exactly that. We actually drop it, and we drop it again, and we drop it again, and again. And we count the number of favourable outcomes, that is, the number of times it lands butter side down, and we divide that by the total number of possible outcomes, the total number of times I drop the toast.
So here are the results of our toast dropping experiment. The toast landed butter side down 13 times, out of a total number of drops of 30. So the probability of the toast landing butter side down is 13 divided by 30.
Now, this result is not the same as we would expect it to be theoretically. The buttered side divided by the 2 possible sides is 1/2. So why wasn't the result as we expected? Well, if I drop the buttered toast another 30 times, then this experiment would be slightly more reliable. But I would have to do it several thousand times before the experimental probability got close to the theoretical probability. So, let's summarise. Experimental probability is worked out by repeating an experiment a large number of times and recording the different outcomes. Theoretical probability can be worked out without conducting an experiment. That's it for probability, and it's the end of this programme. Now, if there's anything you found a bit tricky first time round, you can always rewind the tape and have another look. There are also more questions and examples in our Key Stage 3 bite-sized book and on the website. And best of luck with your revision.
For a copy of the current BBC Learning Zone programme guide, send an A4 stamped addressed envelope with stamps to the value of 34 pence to BBC Learning Zone, Current TV, 11 Lakeside, Neptune Close, Rochester, Kent, ME2 4LT.